Hey, this is Mr. Weisfeld. Okay, let's try this summative assessment over again. Circuits and electrostatics. First of all, question number one. Actually, let's do black here. There we go. Okay, so a very small conducting sphere in air. So let's draw a sphere. Maybe it's got some charge on it. It carries a charge of 5.0 picocoulombs. 5.0 times 10 to the... So grab your sheet here. Picocoulombs is 10 to the minus 12. So 10 to the minus 12 coulombs. Coulomb is a unit of charge and is 0.2 meters from another similar sphere, let's say, carrying a charge of Q, big Q. If each sphere experiences a mutual electric repulsion, so I chose positive, positive, because like charges repel. I could have chosen negative, negative. That's fine too. But the force of their repulsion, F of C, is 2.0 micronewtons. Micro is 10 to the minus 6. So 2.0 times 10 to the minus 6 newtons. And the question is find Q. So Q equals what? Talking electrostatics, we're talking Coulomb's law. So this equation right here, the force between two charges or concentrations of charges is K, the Coulomb force constant, times Q1 times Q2, all over R squared, the distance between them squared. So we said that this was R here, 0.2 meters. But we're given F of C, and we're given K and Q1. We're not given Q2. So let me write this again, how we have it. We have K, we have a Q, we have a big Q, which is a question mark, and we've got the distance squared. So let's rearrange this in terms of Q. I think you can see that Q equals R squared times F of C all over K times little q. So let's start plugging in what we know. We know that the radius is 0.2 meters, but we need to square that. Then we know F of C is 2.0 times 10 to the minus 6 newtons. That's the force of repulsion that they feel, so micronewton. And then K, again, check your formula sheet. K is Coulomb's law constant here. It's 9.0 times 10 to the ninth Newton meter squares, newtons times meter squared divided by Coulomb squared. And then times the charge that we've got, so 5.0 times 10 to the minus 12 coulombs. So what I would do is I would put this into my calculator. Let's bring the calculator up and just do it together here. So I need that, and I need this, and I need this here. Okay. So I'm going to turn my calculator on here. All right. Okay, on. I'm going to clear it. Let's see. Yeah. Okay, there we go. Clear. Cool. All right, so 0.2 meters squared, 0.2 squared times 2 times 10 to the minus 6th. I use the double E notation, exponential. I think it's called engineering exponential notation, but anyway, 2e to the minus 6 divided by 9 times 10 to the ninth. Divided by 5 times 10 to the minus 12. That was Jolena. Here we go. I'm coming back to my equation here. I'm gonna maybe see if I need to delete here. So if I delete, I got 5e to the minus 12. Alpha lock is on. Okay, 5e to the minus 12. So let's read over this again. 0.2 squared times 2e to the minus 6 divided by 9e to the 9th divided by 5e to the minus 12. Okay, here we go. So we're getting there almost here. I've got 5e to the minus 12. And I've got 90 to the 9th and 2e to the minus 6. Hey, you know, it's okay. Double check a couple times. That's fine. Enter. Here is what we think is an answer. 1.8 times 10 to the minus 6. And the units are, if you look here, newtons cancels newtons. Meter squared cancels meter squared. Coulomb squared on the bottom. There's one coulomb cancel, so coulombs come up. 1.8 e to the minus 6 coulombs. 1.8 times 10 to the minus 6 coulombs. So we think that's the charge on the other sphere that causes an electrical repulsion of that magnitude at that distance between two conducting spheres. Next question. Let me scroll down here. We'll get started. Question number 2, problem 19, page 650. A pure gold wire, it has a 1 millimeter by 1 millimeter cross section. So let's imagine a wire that is square and pretty small, so 1 millimeter by 1 millimeter. The cross-sectional area will help determine how much resistance is naturally in the wire. So we've got a good start. We think we're going to probably use this equation here. Resistance is the resistivity times the length of the wire divided by the area. So let's make a plan here. So I've got current density, how much amps I'm getting per square meter in the wire. That number is right here. It's 1.0 mega amps per meter squared. So let's make a little note here that we've got current density I divided by A, 1.0 times 10 to the 6th. That's mega. Double check here because Mr. Weisfeld messed up here. 1.0 times 10 to the 6th mega amps, which is coulombs per second per meter squared. So 1.10 to the 6 amps per meter squared. But remember, an amp is a coulomb per second. We'll need that for the next part of this question. But if I've got 1.0 times 10 to the 6 amps per certain meter squared, all I need to do to get the current, the pure current, is to multiply I over A times A. That's the area of the wire. The area of the wire is going to be 1 times 10 to the minus 3 meters, because that's what a millimeter is, a thousandth of a meter. 1 times 10 to the minus 3 meters times 1 times 10 to the minus 3 meters. That equals 1 times 10, add the exponents, 10 to the minus 6 meters squared. That's the area of the wire. So if I take 1.0 times 10 to the 6th amps per meter squared, that's the current density, and I multiply by the meter squared, I should get straight amps, which is 1.0 times 10 to the minus 6th meter squared. That comes out to be minus 6 plus 6 is 0. This is just going to be 1.0 amps, which is 1.0 coulombs per second. So now if we're asking how long will it take for an amount of electrons equal to Avogadro's number to pass a point on the wire, well, we have to know what Avogadro's number. That's number Avogadro. That's 6.02 times 10 to the 23rd, and that's a pure number. That's just a lot of stuff. So if I have so many electrons, so 6.02 times 10 to the 23rd electrons, but I know each electron has a certain amount of charge in coulombs. That's on your formula sheet. So electron charge, a charge on an electron, 1.6 times 10 to the minus 19 coulombs per electron. So we're making kind of a units problem here is what we call it. 1.6 times 10 to the minus 19 coulombs per electron. Notice that we'll get coulombs out of this. So many electrons gives me so many coulombs. If I've got in 1 second 1 coulomb, and I want to know how much time it's going to take to get these, I can just take this current and invert it. So in 1 second I'm getting 1 coulomb. What I think I'm going to have left when I multiply this out is electrons are going to cancel, coulombs are going to cancel, and I'll be left with just seconds. So some probably large number of seconds, which tells me that it will take maybe a large amount of time in seconds for a mole. This is a mole. Remember, a mole is like a dozen, right? In chemistry, it's just a large number of things. And let's get our calculator back here. So let's turn this on. All right. So let's multiply this out. I've got 6.02 times 10 to the 23rd times 1.6 times 10 to the minus 19th, and then times 1. This is going to be seconds. We've already done the unit, so let's put that in there. 96,320. So if I divide by 60 seconds in a minute, 60 minutes in an hour, I should get how many hours. So let's divide by 60 to get to minutes, and let's divide by 60 again to get to hours. So 26.7 hours. So let's write this down. 96,320 or 26.8 hours. I rounded that up. So almost a full day. Granted, this is a pretty little wire, and you would not use a wire maybe this small for anything useful. But it will take a finite amount of time for a large number of electrons to go through that wire. And remember, it would bump in some from one end and some more would spill out the other end. It's not necessarily electrons going all the way down this wire. Alright, so I added something to this question. Check this out. So suppose gold, that's what we're dealing with, this is a gold wire, has a resistivity of 2.2 times 10 to the minus 8 ohm meters. That's how you say that, because that's an ohm and that's a meter. What voltage is needed to produce this current in a length of 1 meter of wire? So remember, our current from this up above problem is 1.0 amps. Remember that our resistance is given by this equation on our formula sheet, the resistivity times the length divided by the area. So the resistivity of this wire is going to be given by, the resistance is resistivity times the length divided by the area. And of course, Ohm's law is going to give me the voltage I need. Voltage is current times resistance. My current is 1.0 amps. My resistance is resistivity times the length divided by the area of the wire, which we said was 1.0 amps times 2.2 times 10 to the minus 8 ohm meters times the length, which we said was 1 meter, and then all divided by the area of the wire. We said the area was this number right here, 1 times 10 to the minus 6 meters squared. So 1 times 10 to the minus 6 meters squared. This is all going to give me volts. So amps times ohms is volts, and meter squared is going to cancel, so the unit to check out, let's plug this in. I've got 1 amp times 2.2 times 10 to the minus 8 ohm meters times 1 meter length of the wire divided by 1 times 10 to the minus 6 meter squared. Put that in, and you get that a voltage of 0.022, sorry, yeah, 0.022 volts. Not a very large voltage to create that much current. And then let's go down a little bit here. So the next part of the question is, what is the power? So here's the reason why I put this question in the quiz. We haven't talked a lot about the wires in a circuit having resistance. And the point is, what is the power dissipated in a wire? So power, once again, on our formula sheet is I times the change in voltage. So we think that the voltage drop across this wire is going to be the power equals the change in voltage times the current. And we know the current equals 1 amp. I equals 1.0 amps. And we know that the change in voltage is this number right here, 0.22 volts. So I've got 0.022 volts times 1.0 amps, and that equals 0.022 watts. Watts is the unit of power, so volts times amps is watts. Okay, so that was question number 2. Let's go on to question number 3. I have a circuit with 2 bulbs. I got a 12-volt battery, and I've got an 8-ohm bulb and a 12-ohm bulb. And the question is, what is the current in the circuit before and after the wire is clipped on at C and B? So this is called an alligator clip, and what we're going to do is we're going to clip it right here. So essentially, this is called a short circuit, which means you are presenting to the current a path that is way less resistance, so much less resistance in a wire than a 12-ohm bulb, and so we expect the current to follow the path of least resistance, and so we expect the current initially to be going this way, which is fine, but then once you connect this, we'll find the current is going this way down here through the wire, and all of that can be shown either in an experiment here in the classroom, or you could derive that based on the resistance of 2 branches. You would find if you did the calculation of how much current would go here. The current would go based on the resistance, and the resistance there's much less, so very little current, if any, through the 12 ohm bulb. Okay, so that is kind of the answer to what I think is going to happen to the 12 ohm bulb when the wire is attached, because a short circuit provides a path for the current that is less resistance. The battery has negligible internal resistance. That's just to say that you can count on 12 volts pure and simple coming from the battery. So we make, without the short circuit, so as drawn, without the clips in there, we want to find the equivalent resistance of this circuit. And since we have a series of resistors, the equivalent resistance is one resistance plus the other. So we find that the equivalent resistance would be 8 ohms plus 12 ohms, which would be 20 ohms. And then we would use Ohm's law to say that the voltage equals the current times the resistance. Or, of course, put another way, the current, let me put a real proper I here, is the voltage divided by the resistance. So you would draw your little thing, just remind yourself, current equals, voltage over resistance. So what I get when I do that, I would say there's 12 volts, that's the driving force on the circuit, divided by 20 ohms. And I think you would find that that's, let's see, 4 goes in, so that's 3/5 of an amp. So now, if 3/5 of an amp is going through the 8 ohm resistor, then 3/5 of an amp is going through the 12 ohm resistor by conservation of current. It's not building up anyway. So 3/5 amp through the 8 ohm bulb and 3/5 amp. I guess I could say that that's 0.6 for those of you that want a number. That's fine, 0.6 amps. Then the voltage across the 8 ohm resistor would be voltage equals current times resistance, I times R. So that would be 0.6 amps times 8.0 ohms, or 4.8 volts. Now, I know that the rest of the voltage better add up to 12, but let's just walk through it. The voltage through the 12 ohm bulb is current times resistance, so that's going to be 0.6 amps times 12.0 ohms. And so that's going to be, I think, 7.2 volts. And notice that these have to add up to 12 volts, which is conservation of energy. The energy that the battery puts in, remember this escalator of energy into electrons, has to be perfectly and completely diminished when it gets around to here again, and we imagine that there's some kind of ground here, so 0 volts or some kind of starting point. The power dissipated in the 8 ohm bulb, power is going to be P equals V times I, or remember it's I squared times R, or remember it's V squared over R. You can pick which one of these you like. I kind of like I squared times R because I know the current pretty clearly. So it's 0.6 amps squared times the resistance, which is 8 ohms. And let me just double check this on the calculator because I don't want to mess up here. 0.6 squared times 8. 2.88. And the units for power? 2.8 watts. 2.88. Let's say 2.9 just to round it to 2 places. 2.9 watts. That's the power dissipated in the 8 ohm resistor, and we would expect uh, more power to be dissipated in the higher resistance bulb. So again, let's do power equals I squared times R, which equals 0.6 amps. Remember, there's the same current in both bulbs, times 12 ohms. I didn't put ohms here, but these are ohms. Equals, again, double check, 0.6 squared, that's the current, times 12, 4.3, let's say 4.3 watts. Okay, so let's clean this up a little bit. I've got 0.6 amps here, same current through both resistors, same current through both bulbs. I've got the voltage adding up here to 12. Higher voltage through the higher resistance bulb, lower voltage through the lower resistance bulb. And then I've got power here, 2.9, and then 4.3. So now, I clip the circuits, which just means I short circuit the 12 ohm bulb. And the question is, what's the current through the 8 ohm bulb? So current, V equals I times R, or V over IR. When I want to know the current, it's voltage divided by resistance. So I've got current equals voltage divided by resistance equals 12 volts divided by 8 ohms. Remember, there is very little or negligible resistance through a wire. So this is going to be basically, I've got 3 4s up top and 2 in the bottom. So this is 3 halves of an amp, which is more than 0.6. This is 1.5 amps. The current through the 12 ohm bulb is short circuited. There's no current, 0. The voltage across the 8 ohm bulb, voltage equals current times resistance, equals 1.5 times 8, 1.5 amps times 8 ohms equals 12 volts. And that makes sense because the voltage that you increase through the battery is the voltage you dissipate through the load on the circuit. So 0 voltage across the 12 ohm bulb. And then in the power dissipated, so power equals voltage times current. We could do it this way if we wanted to. We know we're losing 12 volts in the battery, and we know the current is 1.5 amps. So we've got 1.5, 18 watts dissipated in that one bulb. And in the 12 ohm bulb, once again, we've got 0 watts dissipated because there's no current through that bulb. Alright, so let's move on. Question number 4, last question. Determine the equivalent resistance of the circuit between points A and B. So we've got a couple equations. We know that series resistors add, and we know that parallel resistors it's the sum of the reciprocals, the reciprocal. So let's tackle this bit here first. These resistors are all in parallel. That means the equivalent resistance of that branch is 1/2 plus 1/3 plus 1/6 plus 1 over 1, all to the -1. So I think you'll see that 6 is the common denominator here. So what I've got is 3 plus 2 plus 1 plus 6 all over 6. right, to make it, and then negative 1. So that's 5, 6, 12 over 6, which is 2. Sorry, 12 over 6. Got ahead of myself. 12 over 6 is 2. Negative 1 is 1/2. So the equivalent resistance of this branch is 1/2 of an ohm. This double checks, so double check the equivalent resistance of parallel resistors, these are parallel, is less than any one resistor. So 1/2 is definitely less than 1 and 6 and 3 and 2. Then you have this circuit. So very important to simplify the circuit as you're going. And this is A to B. You have a 5 ohm resistor, and then you have a 1/2 ohm resistor. Since these are series resistors, the equivalent resistance is 5 plus 1/2, which equals 5.5 ohms. Remember that the battery or whatever circuit this is in doesn't know any different. It put a current in here and it sees 5.5 ohms. It doesn't matter how the current's going. It doesn't matter what's happening. It all looks like a 5.5 ohm circuit. So, nice job. Thanks for listening.